Okay, so what would the corresponding rule for subtraction look like? Well, we'll write it down now. So similarly, the derivative with respect to x of the difference between two functions f of x and g of x, so that's what it means to take two functions f and g, subtract them at each point x, so you've got f of x minus g of x, and then take the derivative of the resulting expression with respect to x. That's what this notation means, and it turns out that you can calculate this by taking the derivative of f of x with respect to x, because that's of course what this notation means, and then subtract the derivative with respect to x of g of x. So that's a rule that tells you if you want to take the derivative of a difference of two functions f and g, you can just take the derivative of each function separately and then subtract afterwards. That's what that rule is telling you. And to see why that's true, I'm not going to prove that one to you, but I will tell you that the proof is very, very, very similar to the proof of this rule that we just did at the end of the last video, right? You can follow these calculations almost exactly. The way you can do it is just define your capital F to be f of x, but instead of doing an addition like we did here, do f of x minus g of x. And then follow these calculations and see what you get. And what you're going to end up getting is f prime of x minus g prime of x. And that's how you can prove that this rule is true. Okay, so another rule that we'll talk about, and this actually is probably going to be everyone's favorite rule for the first little while. This rule does a lot of work for you. This is called the power rule, and what it does is it tells you how to take the derivative of a function that appears in the form of a power. So let's write a function like that down. Let's say I had a function f of x, and I had it equal to x to the n, so some power of the variable x. And let's say that n is, really to be clear, n has got to be a constant in this case. So for some constant real number n. Okay, so that's what you have in the background. And what the power rule tells you is that f prime of x is given by the following formula. It's just n times x to the n minus 1. Okay, and that actually takes quite a bit of work to prove. It's a consequence of the binomial expansion theorem. And if you combine the binomial expansion theorem with the limit definition of the derivative and you carefully work it out, it's a bit technical, but you'll end up getting exactly this. So the details behind why this rule works are in the complete notes. If you find them in my Google Drive folder, the complete notes contains a complete proof of this rule. I'm not going to include it in these videos, but it is true because of the binomial expansion theorem. And if I were to rephrase this rule in operator notation, just because I have been doing that for all the other rules, I would word it like this. I'd say, so in other words, that is the derivative with respect to x of x to the power of n is equal to nx to the n minus 1. Okay, so that is another way to phrase the power rule. But again, this has to be understood to apply to only the case where your power, the exponent here, n, is a constant. Okay, so just a quick summary. These are the rules we've got. On the previous page, we have the derivative of any constant function is equal to 0. This rule says that if you have a constant multiplier on a function and you want to take the derivative of the result, you can pull the constant multiplier right out of the derivative, like we can see over here. So constants can be pulled out of derivatives. The next rule that we talked about says that derivatives can be broken up over sums. Right? If you have a derivative of a sum, you can write it as the sum of derivatives. And then this other rule that I didn't prove to you, but I'll leave it to you as an exercise to justify the details. The derivative of a difference is the difference of derivatives. You can take the derivative of each part separately and then subtract afterwards. Okay, and then the power rule came after. I would suggest that you have a separate sheet of paper and you write all of these rules down and have them handy, so you don't have to go flipping through your notes to find rules. It's just a little bit of a time saver, and it's also a good note-taking principle to have your own your own formula sheet. But let's look at an example of how we can apply this. Really what we have now is we have enough rules to make taking the derivatives of any polynomial function fairly straightforward. We don't have to resort to the limit definition anymore ever again if we have polynomials. And I'm going to show you why that's the case with this example. So we've got some examples. Find the derivatives of the following functions. And you can see there's 5 functions here. The first one, let's start with the first one, a. f of x is equal to 4x cubed plus 2x squared minus 1. So we're going to start with that one. And the way I write down the first couple of examples, admittedly, is not going to be probably the way most people do it in practice, but I am imploring you to follow me in the way I write this out for the first couple of examples, because it's so illuminating and it helps so much to really make it clear to yourself and to whoever's reading your work how exactly you're applying these properties, and I promise you it'll lead to a better understanding. And then as we get towards the end of the list, I'll show you a way that you can streamline it a bit and make it go a bit quicker. But for now, let's write it out in absolute detail, because it's really illuminating to do so. So we want to find f prime of x, because that's what it means to find the derivative, right? This is the derivative of the function f at the point x. That's f prime of x. That's what it means. Okay, so the first step I'm going to do is only going to be a shift in notation. So if f of x, or pardon me, if I should be pointing up here, if f of x is equal to 4x cubed plus 2x squared minus 1, then f prime of x is the derivative of this function, right? So I'm going to actually write out the derivative of this expression using operator notation. So I'm going to write this as the derivative with respect to x of 4x cubed plus 2x squared minus 1. Okay, and then now I'm going to use two rules actually. I'm going to use two rules at once. First of all, this rule says we can split up sums, right? If I have the derivative of a sum of two functions, I can split it up as the sum of two derivatives. And then this rule at the top of the page, I know I've said this a few times, but it doesn't hurt to repeat it. The derivative with respect to x of a difference of two functions can be broken up as the difference of two derivatives. Basically, what that means is we can split this derivative up term by term and take the derivative of each term separately, right? So that's what we're going to do here. So the next step is going to be the derivative with respect to x of 4x cubed. Then I'm going to say plus the derivative with respect to x of 2x squared, and then minus the derivative with respect to x of the constant function 1. So we just split this up term by term. Okay, and now we're going to apply this constant multiple rule, this rule over here. And you might be able to see now why I was so biased towards writing these rules in operator notation, because it's a little easier to see how they're being applied. Because now I have the derivative with respect to x of a constant times a function. That's what we have here, right? 4 times x cubed. Think of this as the 4 and the x cubed. Well, this rule just says the 4 can come right outside, and then you just take the derivative of the x cubed afterwards, right? So that's what we're going to do here. So the next step will be, I'll pull out the 4, so I'll get 4 times the derivative with respect to x of x cubed. And then here, I'll do the same thing, but I'll just pull the 2 out. That 2 can come out in front. So this is plus 2 times the derivative with respect to x of x squared. And then what about this? The derivative with respect to x of 1, which is a constant. This is a constant function. So actually, our very first rule is going to kick in, right? If you have the derivative with respect to x of any constant, you just get 0. So we can apply that here. This is just going to be 0, so let's stop writing it. This is just minus 0. Okay, which doesn't do anything. But now, okay, now we've boiled it down to the only derivatives now we have to take are the derivative with respect to x of x cubed and the derivative with respect to x of x squared. And that's where the power rule comes in now, because we have this following formula we can use, right? If I have the derivative with respect to x of x, say x cubed, where n is equal to 3, then I would just write this as 3x to the 3 minus 1, which would be 3x squared. So that's that. We're actually going to use this power rule to work out these two outstanding derivatives that we have to find, the two derivatives that are left to compute. Okay, so for the x cubed one, we're going to have 3 times x squared. And all I'm doing is just applying this rule with n equal to 3, because we're talking about the derivative of x cubed, right? So take 3 in place of the n, and you've got x cubed inside the derivative. The derivative is going to be 3x to the 3 minus 1, that's 3x squared. So that's how I got this. Okay, what about the 2 times the derivative with respect to x of x squared? Well, I'm going to have plus 2 times what? Well, go back up and apply this formula. If you have x squared in here, then that means your n is equal to 2. So you have 2 times x to the 2 minus 1, that's like 2x to the 1. Okay, and then this minus 0 isn't doing anything. Let's just ignore this now. I won't bother copying the minus 0 on the next step, of course. Right, so now, well, we can clean this up a bit, but the derivative is done. Right? We finished taking the derivative. So what do we get? We get 12x squared plus 4x. Right, so that's how we can finish that one off, and we can say, if we want to summarize the answer now, we can say therefore f prime of x is equal to 12x squared plus 4x, and that's how you can finish that one off. Okay, and that's an example of applying all these rules of differentiation to take the derivative of a function. Imagine if we had to use the limit definition of the derivative for this. Take the limit as h goes to 0 of f of x plus h minus f of x all over h as h goes to 0, right? Imagine how annoying it would be to work out f of x plus h here. It would be really, really tedious. I'd have to turn the page sideways because my lines would be so long as I was working the steps out. There'd be so much expansion to do. With all the brackets, it'd be easy to make a mistake. So it'd be a lot more work than we really need to do. So that's why it's nice to have these rules. This is much more efficient, and we didn't have to even talk about limits, right? It's not that limits aren't happening. The limits are behind these rules, and they're the reason these rules work, but it's nice to not have to use limits to evaluate these derivatives.